x minus x2 this time over x1 minus x2 plus same term but same pattern but for x2, right? So what would it be? It would be x minus x2. No, it would be x minus x1 over x2 minus x1, and then x minus x. No, okay, wouldn't be that. It would be, so upstairs, I'm trying to get a hold on the pattern because I'll have to. The next step is to figure out the pattern, right? So you have the value here. Just going to explain what's supposed to happen. The way you get this thing. When x is equal to x0, you want only this term to contribute, and you want this to be equal to 1, this to be equal to 0, and that thing to be equal to 0. And same for x equals to x1, but with the middle term, and x equals to x2 with the third term. So how do you achieve that? Well, when x is not equal to x0, when x is equal to x0, these terms cancel and you get 1. And the same with this. And here you get 0, and the same term here you need to get 0, so it's going to be x minus x0, right? You need that term to cancel every other term, and then you have to divide by x, by the thing it has to be when this term is active, so that this is 1. Okay, and you have another similar factor for, so x minus x1 over x2 minus x1, right? This is what happens. This is the pattern we want. You have a sum of different terms. Each term is the value of the function you want for a specific value of x times a lot of factors that become 0 when x is equal to the other points that's not in this term, right? And it's equal to 1 when x is equal to x0. So how do we know that this works? Well, it's a polynomial of degree 2 because you only multiply things. So this is not just a number, just a number. You have x here, you get degree 2. Same thing over there, you add degree 2s, it's still degree 2. Okay, so you have just a big degree 2 polynomial. So it's like c plus b x plus a x squared, right? That's what degree 2 means. It could be degree 1, but in that case it's just the leading term is equal to 0. That's fine. So you have a degree 2 polynomial. You have 3 distinct points. There's only one degree 2 polynomial which goes through 3 distinct points. That's a rule. You have 3 equations and 3 unknowns, and it's a linear equation, so that's how you see it. So okay, so you have a polynomial expression which goes through all of the points, and it's the only one, and it's the smallest degree. It's always going to be the smallest degree, because in order for this term, even if you get more points, I mean, in order for this term to equal to 0 whenever you hit any of the other points, you need one factor for each other point, right? Each factor contains x. So the polynomial you get is at most the number of points minus 1, right? That's the degree of the polynomial at maximum. And then you sum it all up, and it's so always going to be the smallest polynomial. But since we have this in the program, the notion of a polynomial, we don't have to we don't actually have to compute it every time. We don't have, if you give me x, I don't have to redo this whole computation every time. It's fine if you give me the same table of values for f, and then you give me a lot of different values for x. I can compute this into a polynomial and then use evaluate polynomial to get the value. Is it going to be faster? It's going to be a little bit faster, but you shouldn't expect like a huge speed up, but it's actually a more powerful way of looking at it that's almost never less fast. If you need just the table, just to store the function in the table of values, when you convert it to a polynomial, you're basically converting it to a different table. So it's still an array in memory, but now it's an array that you can compute. You can evaluate the value of the function faster. That's all. And you can also derive it, and you can do stuff with it. But you have to compute. You have to transfer it from one way of representing it, so one representation, to another, to be able to do that. But there's also another way in which this can be useful, is to have just this big table of values, this huge range, and then just look at small subtables. So, and by table I mean array. So you have this 1,000 points, right? If you fit a polynomial to 1,000 points, it's not necessarily going to be pretty, right? It's going to probably be pretty nasty. Because 1,000-degree polynomials are just messy. They could be anything, and they don't have to be. They're not necessarily good approximations of your function between the points. But if you instead take the approach of looking at this approximation locally and say, okay, I have 3 points here, 3 points here, 3 points here, 3 points here, so on, and then on these 3 points here is a polynomial, on these 3 points here is a polynomial, and so on, then you can compute this every time on demand. Or if you want to get fancy, you can sort of make a table of polynomials, so a table of tables. Use that. So there are some applications. Now though, let us just take a table of values actually let us write this struct that encapsulates this idea, and then we'll be out of time. We're actually out of time right now, but let's do it anyway. Type def struct and then so you have x0, right, which is a double. You have h and int n, the total number of points, right? And then you have let's write it like this. So it's a pointer. So f is going to be the address in memory of a place that can hold a double precision number. But because of the way C works, if you give it the address, you can, and because the memory in the computer is an array in itself, you can sort of start at some place and then keep track of how many things you have and never go beyond that, and that chunk of the memory is your array. That's how you do it in C. And then table func table, probably better, you know, like this. But if I write it like this, people might actually think it means something. So we could write like functions to initialize it. Func. Let's write it func t. So func t. We want to pointer to that. F. Yeah, that might. I don't know. F pointing to F. You see, bad choice there. Is equal to double pointer malloc n times size of double. Note how tedious it would be to redo everything if instead you've decided, okay, my program doesn't run fast enough, I'm going to try to reduce significantly the precision to just take less space in memory. So instead of using double precision numbers, I'm going to use simple precision numbers or floating point, like you write it float in C. Notice how tedious it would be. You'd have to just change everything, you know, just double to float. But maybe not everything, you know. There could be a place where you need doubles, and so you have to go through really to make sure you don't introduce any mistakes.